Alrighty. Good afternoon. Welcome back. I hope you guys all had an excellent weekend, that you got some time to relax, and that you're doing well. That you had a nice beginning to your week yesterday. I hope you guys are good. As you all know, grades were posted yesterday. They should be live in Synergy by this point. I don't know when they actually send out the progress reports, but the grade in Canvas is the most accurate grade you can refer to as far as yourselves are concerned, but that should be the same as in Synergy right now. I tried to grade everything I could up until like Monday morning, because I need to submit grades by noon on Mondays on those days when they're due. And that's what I did. I got them all in at like 15 minutes before noon. So, I gave y'all every opportunity. That being said, excuse me. If you're not happy with the grade, maybe you have missing stuff, you still have time, right? We have roughly 12 weeks left in the semester. That's not including like spring break and other holidays that might come up. So there's still time. If your grade was not approved on a self-assessment on the free response questions, please look back at the feedback, make corrections, resubmit, get a better grade. If you're not doing well on the multiple choice questions, look back over them, do them again. Ask me for help on them. I'm more than happy to help you guys. I'm not going to give you the answers, but I'll help you. So, you've still got time. There's resources. I myself am a resource, right? Come to office hours on Mondays if you can. Those are all options. Also, over my course of grading, specifically with the Chapter 6 free response questions, mostly because there's just a larger number of those turned in at this point. A lot of these had the same mistakes as far as like equations looked the same errors, same type of writing. You guys get what I'm getting at? It appears as though you guys are finding the same resources to get help on these questions, or you were helping each other, and that's all fine. It's all fair game, guys. I know that if you are stuck, you might be typing the questions into Google, seeing what you can find. I get it. I've done it. Totally fine. I'm not going to stop you. I'm not going to penalize you because I found that you were doing that. It's part of the game. It's part of how it works. You're going to try and figure these things out as best as you can in any way you can. Good. That's fine. The caution is that you need to understand what you're doing. Some of you had methods listed that are not in the scope of this course. And, it's fine. Maybe you're learning something new. And some of you just didn't check the math. You didn't put it in your own calculator, or if you did, it was input incorrectly because maybe it was written in an odd way. You weren't sure how to put that in the calculator. And that's going to happen. These are some new functions and things. But I do need to warn you that, so the questions that I use on the free response questions are from AP. They're from College Board, so they're like copywritten. They're not supposed to be out there on the internet on these websites that provide solutions. They are. There's no way for them to like stop that entirely. And nothing stops you from posting to those sites and asking for help and solutions. And again, it's a resource. It's out there. You're welcome to use it. However, what College Board and some teachers who teach AP and professors who are part of these courses in grading, they are actively looking for these questions online. Right? They do Google searches and see who's posted for them, or they're part of those websites that provide solutions, and they are actively providing incorrect solutions. All right, I found this out because of some Facebook groups that I follow as far as teaching AP stats and AP teachers, and that was a whole thread of comments this weekend. So again, feel free to use these resources, but number one, make sure you understand what's going on, like the math that's being used. If you don't understand it, don't use it. And if you don't understand it and it's something we've done in class, ask me to explain it more. Send me an email. Ask me to explain it, okay? Stay after class and ask me to explain it. Come to office hours, whatever. I'm more than happy to help make sense of these things and these equations. So make sure you understand the math that's being used and check it. Don't just copy it blindly, right? Check the math. Put it in your calculator. See if you can get the same result. Right? If you can't, or if you're not getting the same result, then either their equation is wrong, there could be some sort of input error on the calculator, or you got the right answer and they put a wrong one in there. Okay, so I want you guys to be aware of this, that this is out there. Okay, just because you found a solution online does not automatically mean it is correct. So that's my warning, that's my spiel. I want to be transparent with you guys and let you know that I do see these things when I see a bunch of the same thing happening. I try to figure out why. That's my mathematician brain. I see the pattern. I want to know why there's a pattern. I try to find a reason. This is the best I could come up with. And, you know, use whatever resource you can to understand the material, to get assignments turned in. I get it. I've done it. It's part of the process. No issues here for me on that. All right. Is there any questions or anything about grades and all of that that I've just talked about? All right. Okay. Excellent. So then we are going to be moving on to section 8.2 today. I had originally planned to try to do section 8.2 and section 8.3 in one day so we could complete it this week. That's not going to happen. There's too much going on in sections 8.2 and 8.3. They need their own time. So it's adjusting our calendar just a little bit to accommodate that because we need the time. That's just how it's going to be. So we're going to get into this lesson here. Please have something available to take some notes on. There's some things that you will want to have in your notes. It's not going to be a ton that you need to write down. We're going to look at some examples, but there's some conditions and formulas that you're going to want to have reference to. Excuse me. All right, so here we go. We are in Chapter 8, Estimating with Confidence, and we're doing Section 8.2, Estimating a Population Proportion. This is our goals for today. We want to be able to state and check the random 10% in large counts condition for constructing a confidence interval for a population proportion. We need to be able to determine critical values for calculating a C% confidence interval for a population proportion using a table or technology. Construct and interpret a confidence interval for a population proportion. And we want to be able to determine the sample size required to obtain a C% confidence interval for a population with a specified margin of error. We will see examples of how to do all of this today. There will be some examples in the slides, and I have 2 other example problems ready for us to go through as well. As on some of the reflections in our self-assessments, many of you guys asked if I could do more examples during class time, so I'm going to be providing that, or at least doing my best to, so that you guys can see more and have a better understanding. So first, this is something you're going to want to have in your notes here. Conditions for estimating P. Right? Before constructing a confidence interval for P, you should check some important conditions. They're here. Conditions for constructing a confidence interval about a proportion. It must be random, meaning the data came from a well-designed random sample or randomized experiment. If you see in the context that so-and-so took an SRS of 25 people out of the population, that's random. If it says, you know, so-and-so took a poll by asking the first 30 people who walked in the front door their opinion, that's not random. That's convenient. All right, so it fails the random condition. Right. We need to check the 10% condition when sampling without replacement, which is typically what's going to happen. If we're not sampling without replacement, in other words, we're sampling with replacement, we don't have to check the 10% condition, because essentially we have unlimited, it works out differently. And we need to check the large counts condition, meaning that both n p hat and n times 1 minus p hat are at least 10. The number of successes and number of failures are both at least 10. That's the goal. You raise your hand if you need a moment to write any of this down. Constructing a confidence interval for P. We can use the general formula from section 8.1 to construct a confidence interval for an unknown population proportion P. Right, so this right here is what we saw last week. Right, for constructing a confidence interval, we take our sample statistic and we add and subtract the critical value, how many standard deviations I want to be within the actual proportion or parameter, times the standard deviation of the statistic. And this is what we did last week. The sample proportion p hat is the statistic we use to estimate p. When the independent condition is met, meaning one outcome has no effect on the next outcome, the standard deviation of the sampling distribution of p hat is given like this. Sigma p hat equals the square root of p times 1 minus p divided by n. However, this is assuming that we have p. Since we don't know p, we replace it with the sample proportion p hat. This gives us the standard error of the sample proportion. Right, square root of p square root p hat times 1 minus p hat divided by n. It's the same exact formula. We're just replacing p with p hat because that's the information we can work with. That's what we have. And instead of calling it a standard deviation, we call it the standard error. Right, we can use that notation SE equals this square root thing, or we can use lowercase s subscript p hat. You might see both of those within the textbook. Okay. When the standard deviation of a statistic is estimated from data, the results is called the standard error of the statistic. Right. Raise your hand if you need a moment to write anything down. So in order to calculate our confidence interval, we have to find the critical value. Right? Within how many standard deviations or standard errors do we want to be of our statistic? So how do we find the critical value for our confidence interval? Right? We have our same rule here. If the large counts condition is met, we can use a normal curve to find a level C confidence interval. We need to catch the central area C under the standard normal curve. So here we have a standard normal curve. We're capturing the middle 95% of our curve, which leaves 2.5% to each side. We have 5% left over. Half of 5% is 2.5. We split that evenly between the two tails. To find a 95% confidence interval, we have used a critical value of 2 based on the 68, 95, 99.7 rule. Using table A or a calculator, we can get more accurate critical values. All right. Using table A, the critical value we can find is negative 1.96 or 1.96. And rather than calling this a z-score, because it's not necessarily a z-score, right? We call this critical value z star. We use a little asterisk. And it is 1.96. It's just the positive value of whatever we found on table A for a 95% confidence level. Now, when we find this value, we're always going to find a negative z on table A, because table A gives us proportions to the left of a value. Right, so when we're looking for 0.025, we're finding the 0.25 that's over here on table A, which is with a negative z value. Right? And then we just turn it positive because we're using distance, and distance is always positive. Does anyone need a moment to write anything down, or do you have any questions so far?
It's okay, you can go, it's okay.
Sure? I go back just as easily.
I was just going to ask if you could re-explain the, like using the picture, because I'm kind of confused a little bit.
Okay, so in the picture here, we have our standard normal curve, right? And we've highlighted here to the left and to the right, the area of the two tails, right? And we have symmetry in this curve. And since we're catching, so to say, the central area, the central 95%, that means we have an equal area to each side of that central part. So we split the 5% between the two tails, 2.5%, 2.5%, which as a decimal is 0.025. When we go to table A and find 0.025, which will be, where's the closest we get to 0.025? Right here. Oh, we actually hit it right on this. Right? We have 0.025. On table A right here. That corresponds with negative 1.9 and 0.06. So we combine those two and we get negative 1.96. Okay, and so that's what we see as z star over here. Z star equals negative 1.96. The other side of the interval is the positive z star of 1.96. Right? So unlike a z-score, where the z-score can be positive or negative, right? Z star is a distance, so we can have positive or negative z star, right? But the value of z star is always a positive number. Did that help?
Yes, thank you.
You're welcome. All right. Oh, we'll see an example here of finding a critical value. So we're going to use table A to find the critical value z star for an 80% confidence interval. We're going to assume the large counts condition is met, which means we can use a normal curve. So since we want to capture the central 80% of the standard normal distribution, we leave out 20%, which leaves 10% for each tail. So we have our picture here again. The middle 80% leaves 10% to the left, 10% to the right in the tails. Right. We're going to search table A to find the point z star with area 0.1 to its left. So we go to table A, and we find these two values are the closest to 0.1. Right. 0.1003 is closer to 0.1 than 0.0985. So we're going to use that value. That means that the z-score for this value on table A is negative 1.28. We get negative 1.2 plus 0.08, negative 1.28. The critical value z star for an 80% confidence interval is z star equals 1.28. So again, we're just using the positive value of whatever we found on table A. And we have that on our graph here. Negative z star equals negative 1.28, positive z star 1.28. And this creates the confidence interval, right? We're 80% confident that, you know, whatever it is we're looking for, right, the true value of that is captured between these z stars. And similar to a z-score, we can work backwards to find that value, whatever it is we're looking for. We'll see an example of that in a minute. Is there anything I can clarify about this example? Does anyone need a moment to write anything down? So once we find the critical value z star, our confidence interval for the population proportion p is still, we're using the same frame for our formula. We get it's equal to p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. Okay. This gives us our interval. We call this method the one sample z interval for a population proportion. This is a method we have, this is an inference method for estimating population proportion. Right? We call this an inference method because it allows us to infer the true proportion based on a sample. Inference. When the conditions are met, random, 10% large counts, a C% confidence interval for the unknown proportion P is P hat plus or minus Z star times our standard error, square root P hat times 1 minus P hat divided by N, where Z star is the critical value for the standard normal curve with C% of its area between negative Z star and Z star. Right. Now, I encourage you to write this down with all of its context and everything for your notes. This formula will be on your formula sheet for the AP exam. All right. If you have a copy of the formula sheet, which I encourage you to have one, if you can print one, great. If you have access to one on like somewhere else, please make sure you know where it is. This formula is on the sheet. However, it's not given all these contexts. It's within this definition here. It's just, here's the standard error of a sample statistic for sampling distributions or proportions. Oh wait, yeah, the entire formula is not on there, sorry. Nope. Nope. Yeah. So you get the standard error formula. I apologize. Not the whole thing. All right, so be mindful. There's lots of things to remember. I apologize. Anyone need a moment to write this down now that I'm done rambling? So let's consider an example. Suppose that you took a simple random sample of beads from a container, a rather large container, and got 107 red beads and 144 white beads. We're going to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. I claim that 50% of the beads are red. It's a container containing only red and white beads. We're going to use the interval to comment on this claim. We actually have a sample proportion because we took a sample, so this is good. So we have 107 out of 251, we have 0.426, so p hat equals 0.426. And our conditions, random, it's an SRS, that's met, 10%. There's a really large container of beads and 251 is less than 10% of that container. And large counts, we have 107 successes and 144 failures, meaning we have more than 10 of each. So our conditions have all been met, meaning I can find a standard error, I can use a normal curve, we have all of our things we can do. Right? So here's our little chunk of table A that we're going to need. For a 90% confidence interval, Z star is equal to 1.645. And this is due to when we have a 90% confidence interval, 10% is left on each side, or 10% is left to split between each side, giving 5% for each side. We get 0.05. These are the two values closest to 0.05. 0.05 is actually smack in the middle of these two values. They're both the same distance from 0.05. So we split the difference. Right? We have negative 1.6 and then go halfway between 0.04 and 0.05 and we get 0.045 and we make that into our decimal. We then use this formula to calculate our interval. We get 0.426 plus or minus 1.645 times the square root of 0.426 times 1 minus 0.426 over 251, which gives us 0.426 plus or minus 0.051. And we have the interval from 0.375 to 0.477, which means we are 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in the container. Since this interval gives a range of plausible values for P, and since 0.5 is not contained in the interval, we have reason to doubt the claim. Right, we have evidence against the claim. Right, we're not saying the claim is incorrect. We don't have the evidence to say that. We have enough evidence to say, I believe that this might not be true. We have doubt. Right, we have to be careful in what we say here. We can kind of be more vague. Right? Is there anything I can clarify about this example? Does anyone need a moment to write anything down? We have a four-step process. The four-step process is something that comes up in the textbook quite often, and it's there because it gives you a roadmap in answering questions in a way that AP and College Board want them answered. Checks all the boxes, so to say. All right, so we have this four-step process to construct and interpret a confidence interval. Step one, state. Essentially state what you will be doing. What parameter do you want to estimate, and at what confidence level? Plan. Identify the appropriate inference method. Check conditions. Do. If the conditions are met, perform calculations. And finally, conclude. Interpret your interval in the context of the problem. The conclude step is something that is sometimes overlooked. All right, you can do all the setup and calculations really well and get the right interval. But if you skip the part where you make a statement saying what it means and how it relates back to the original context of the problem, you're not going to get all the credit. You have to make that summative statement at the end. Tie it all together. Okay. Does anyone need a moment to write any of this down? So the other thing that can happen in these scenarios is we may want to select a sample size before conducting the sample, which means we won't even have a p-hat to use, right? But it might be necessary because maybe we're trying to save money on conducting our poll or sample, right? In planning a study, we may want to choose a sample size that allows us to estimate a population proportion within a given margin of error. Margin of error, ME, in the confidence interval for P is, what we're adding or subtracting to our statistic, right? Z star times the square root of P hat times 1 minus P hat divided by N, right? This is the standard error. Z star, again, is the standard normal critical value for the level of confidence we want. Because the margin of error involves the sample proportion P hat, we have to guess the latter value when choosing N. There are two ways to do this. In other words, we have two options here. Option 1, use a guess for p-hat based on past experience or a pilot study, meaning maybe you took a small sample just to get started to see if there was something that you actually wanted to conduct an experiment or sampling on. Okay, so you have some idea of what the result could be. Or there's a previous result that maybe you're looking to update, right? Maybe there's a result from years and years ago and you're like, okay, well, let's conduct this thing again and see if things have changed. We can also choose to use p-hat equaling 0.5 as the guess. This is because the margin of error is largest when p-hat equals 0.5. So it's kind of using 0.5 will guarantee that the margin of error will be less than or equal to what we want it to be. Okay. And this is all summarized here. So when calculating a confidence interval to determine the sample size N that will yield a level C confidence interval for a population proportion P with a maximum margin of error ME, solve the following inequality for N. Right, Z star times our standard error, square root of p hat times 1 minus p hat over N is less than or equal to ME, the margin of error, where p hat is a guessed value for the sample proportion. The margin of error will always be less than or equal to ME if you take the guess p hat to be 0.5. All right, so at the very least, even if you have no idea what p hat could be, you don't have anything to reference for it, you can just use 0.5. Okay. See an example of this next. You raise your hand if you need a moment to write stuff down. A company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service, measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied. That is, who chose either satisfied or very satisfied, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3%, 0.03, at a 95% confidence level. How large a sample is needed? So the problem that we're solving is we want to determine the sample size needed to estimate P within 0.03 with 95% confidence. We already, from a previous example, know that the critical value for 95% confidence is Z star equaling 1.96. Okay, this is our more accurate estimate instead of using 2 from table A. We don't know what the true proportion P of satisfied customers is, so we decide to use P hat equaling 0.5 as our guess. We don't have any past results to use. We'll use 0.5. Because the company president wants a margin of error of no more than 0.03, we need to solve this equation. We need the margin of error to be less than 0.03. So that leads us to this equation, right? To the left of our less than or equal to, we have what the margin of error should be equal to, right? And we want that to be less than or equal to 0.03. So we have 1.96, right? Our critical value, Z star, times the standard error, which will be 0.5 times 0.5 over n. We don't know n, we'll solve for n, right? So we multiply both sides by square root of n and divide both sides by 0.03. Right, so we end up with 1.96 divided by 0.03 times the square root of 0.5 times 1 minus 0.5, or 0.5 is less than or equal to square root of n. To get rid of our square root and isolate n, we square both sides, which gives us 1.96 over 0.03 squared times 0.5 times 0.5 less than or equal to n. Punching all that through a calculator, we get 1067.111 is less than or equal to n. In other words, n is greater than or equal to 1067.111. If we round this solution, which we will, we're talking about sampling people, we can't have a fraction of a person, we round up. That is because n must be greater than or equal to this value. If I round down, I'm violating the result, right? I'm choosing an n that is not greater than or equal to that. I can't go with 1067 because 1067 is not greater than or equal to 1067.111. It's less than. That's a violation. Can't do that. So I can round up. I can round up to 1068. That's what makes sense in this context. We round up to 1068 respondents to ensure that the margin of error is no more than 3%. And we've answered the question. Okay. Is there anything I can clarify or explain in more detail about this example? And we will see 2 more examples covering all the stuff for this lesson next. Okay. So that brings us to the end of the slides, the presentation here. And now we're going to jump over and look at some more examples. Move some things. Okay. Alrighty. So here's our first context. All right. This is actually one of the contexts we saw last week in our practice problems during class time. And so we have Tanya wants to estimate what proportion of her school seniors plan to attend the prom. She used an SRS of 50. 50 of the 750 seniors in her school, and finds that 36 plan to go. We want to, part 1 here, or part A, identify the population and parameter of interest. This is just a couple of statements, saying what's our population and what's the parameter. More space. So we have here that the population is our 750 seniors. The parameter is the proportion of seniors who plan to go to prom. So that's it. That's all that this one is requiring us to say. Just population of 750 seniors, parameter, proportion of seniors who plan to go to prom. We then need to check the conditions for constructing a confidence interval. Remember, we have 3 conditions to check. Is it random? 10% condition, and a large counts condition. All right, random, yes. Right, the sample was an SRS of 50 students, so random is the condition of being random is met. All right, 10%. All right, we sampled 50 out of 750 seniors. All right, and that is equal to 0.067, which is less than or equal to 10%. So our 10% condition has been met. Lastly, our large counts condition. Since 36 and 14 are both greater than 10, the large counts condition is met. Now, can someone tell me where the numbers 36 and 14 came from and why I'm using them? Anyone? Yes, thank you, Silali. 36 is the ones who plan to go, and 14 is the leftover who don't plan to go, right? From our sample of 50, right? It's from our sample, it's the number of successes and number of failures. A success is considered going, failure is considered not going, right? So it's I'm essentially stating that NP and n times 1 minus p are both greater than 10. That's our condition. So now we want to construct a 90% confidence interval for p, showing our method. All right, so we will use the one sample z interval, because we've only done one sample. For a population proportion, right? We need to find, well, to do this calculation, right, we already have p hat, and that's going to be 0.72, right, and that's 36 divided by 50. We need z star, which we do not have yet. Okay. And we already have n. That's 50. All right, so in order to find z star, we use the normal curve. Right? We're dealing with a 90% confidence interval, or confidence level. Which implies we have 10% left, which then gives us 0.05 for each tail. The standard normal curve. All right, so from previous result, the 0.05 gives us a z-score on table A of negative 1.96. No, 1.6. What is it? 1.645. That's right. Sorry, give an example. Right, that landed us at negative 1.645. Right, we're right in between two values, so we split the difference between 1.64 and 1.65, 1.645. Right, this z-score lands us at a z star, right, critical value of 1.645. Right, and this is all the information we now need to calculate our interval. So we will use the formula of p hat plus or minus z star times the square root of p hat times 1 minus p hat all divided by n. And now let's do our substitutions. We have 0.72 plus or minus 1.645 times the square root of 0.72 times 0.28, 1 minus 0.72, all over 50. We get 0.72 plus or minus 1.645 times 0.0635. Right, that's our standard error. And this gives us the interval 0.0635 6, what is it? I think it was 1, 4. Just getting back in. 616. Sorry. And 0.824. So this is our interval for P. And our last thing here is we need to interpret the interval in context. So we are 90% confident that the interval from 0.616 to 0.824 captures the true proportion of seniors who want to go to prom. Right? We need that extra little part at the end saying of seniors who want to go to prom because that's the context. If we stop at we're 90% confident in the interval from 0.616 to 0.824 captures the true proportion. Proportion of what? We need to complete that thought. We need to give the context. Excuse me. Is there anything I can clarify about this example before we go to the next one? Our next example. We have a national opinion poll found that 44% of all American adults agree that parents should be given vouchers that are good for education at any public or private school of their choice. The result was based on a small sample. We want to determine how large an SRS is required to obtain a margin of error of 0.03. Right, in a 99% confidence interval. We need to answer this question using the previous poll's result as the guessed value for P hat. Right, meaning we get to start with P hat 0.44 from the previous poll. Right, now we're trying to get a margin of error that's within a certain amount. Right, we need to make sure that it's less than or equal to 0.03. Right, so we're going to be using the formula, the rule, right, of our z star times the square root p hat and minus p hat over n is less than or equal to the margin of error. Right, this is the rule we'll be using. Right, and then we have to solve this for n. We'll have values for z star, p hat, and me. So to get started, what we're missing is z star. Right, we need to find the value of z star. Right, we're using a 99% confidence interval. right? And that leads us to a 0.005 for each tail of our normal curve. Okay. That is here on table A. We get 0.051 and 0.049 as the two closest values on the interior of table A for 0.005. So again, we kind of split the difference. We use negative 2.575. We go between 0.07 and 0.08. So we get a z-score of negative 2.575. Which translates to z star having a value of 2.575. All right. Does everyone understand how I got that value? Okay. So now we have the values we need so that we can solve for n. So now we're going to set up our work here. So we're starting with 2.575 times the square root of 0.44 times 0.56 divided by n, which we don't know. It's less than or equal to 0.03. The first step that I'm going to do is I'm going to break apart the square root. And this is based on the property of square roots that hopefully you've seen before. If I have the square root of a fraction, a over b, that's equal to the square root of a divided by the square root of b. I need to be able to break this square root that has the fraction in it so that I can isolate n. So that's the first step that we're going to take here. We're going to say, okay, well, this is then 2.575 times the square root of 0.44 times 0.56 divided by the square root of n. And that's less than or equal to 0.03. So I've rewritten it. I haven't done any calculation. I've just rewritten this in a way that I can now manipulate it. The next step is to multiply each side by the square root of n and divide each side by 0.03. That moves the square root of n to the right and moves the 0.03 to the left. Right, so then I'm left with numbers on the left-hand side and on the right-hand side, which is what I need. Right, so we do this multiplication. This cancels square root of n on the left-hand side. 0.03 gets canceled on the right-hand side. And we get 2.575 square root of 0.44 times 0.56. And some of you might be asking, oh, Mr. Mosley, why haven't you just found the number for the square root of 0.44 times 0.56? You can. I prefer to wait and do all my calculations in one shot at the end to reduce any possible rounding errors. So that's why I do it this way. Right, divided by 0.03 is less than or equal to square root of n. The last thing I've got to do is take the square both sides. Right, squaring the right-hand side gets rid of my square root, and we get on the left-hand side of 1,815.32 is less than or equal to n, which we could rewrite as n is greater than or equal to 1,815.32, which means we round to 1,816. So we get we would need an SRS of size 1,816 to obtain a margin of error of 0.03 in a 99% confidence interval. All right, and there we have it. Is there any questions about part A? About any of the math that was done, how I got any of the numbers, anything like that? So this is an excellent question, Silali. So this context requires that we round up because we're trying to choose a value of n. Right? This inequality here, this inequality says that n must be greater than or equal to this value here. All right. So if I round down to 1,815, then I have violated the inequality, so to say, because 1,815 is not greater than or equal to 1,815.32. Right? So that's why I can't round down. Right? I have to round up to that 1,816 because I'm sampling people, number one. I can't sample a 0.32 of a person. And that it gives us like kind of a minimum number, right, to use, like a whole number. So with these types of problems, most of the time you will be rounding up because n is greater than or equal to. Does that answer your question, Sitlali, hopefully? Awesome, you're welcome. All right, so the next part here. Answer the question in part A again, but this time use the conservative guess p hat equaling 0.5. How much do the two sample sizes differ? So we've done a lot of work in part A already. We're going to keep some of that, and we're going to use a shortcut here. All right, we already know z, right? So to start here, we have p hat 0.5, z star 2.575, right? And the margin of error that we're using is 0.03. The only thing missing is n, which is what we need to solve for, right? So we're going to actually jump in at the very end of our calculation from the part A. Based on our rearranging of this equation, of this inequality, we ended with the general equation, or the general inequality that n is greater than or equal to z star times the square root of p hat one minus p hat divided by ME. Right? And that's what we ended with. Wait, missing one critical part. Put this on giant parentheses and square it. Right? That's what we ended at here to actually calculate our answer in part A. Right? So we're going to jump in and use that, because why not? We've done all the legwork. Let's use what we've already found. So we get n is greater than or equal to 2.575 times the square root of 0.5 times 0.5 all over 0.03, that whole thing squared. We can put this whole thing in our calculator, and we get n is greater than or equal to 1,841.84, approximately. Okay, which we would then round to 1,842. Okay, so the two sample sizes differ by 26 samples. Okay. Because we have 1,842 minus 1,816. I think it's just 26. All right. So that's the other thing that we get once we get more familiar with the formulas, is that we can use them faster, so to say, right? Can get more done. Any questions? Anything I can clarify? Okay. All right. So thank you guys for sticking around for this long. I know it was a very long class today, but I wanted to give you guys those extra examples and these extra scenarios that are a little more complicated than maybe what we see in our traditional examples in the slides. So hopefully that's helpful. The practice problems for 8.2 are available in the resources, as well as the study guide for section 8.2 and 8.3. It's in one study guide for 8.2 and 8.3, and a bunch of resources and videos and things in our resources in Canvas for 8.2 and 8.3. There's a lot of AP Daily videos for these two subjects for estimating population proportions and means. Right. So there's lots of resources. Tomorrow we'll be doing examples like an activity like we have been doing, like our kind of our new pattern here for this semester. So hopefully that will help this make even more sense. Yeah, and other than that, I'll see you guys tomorrow. If there's anything else I can help you with, please let me know. Stick around and talk to me. Have a great rest of your day.